Hi folks, welcome back to Physics with Captain Rod. I'm making this video here to help give you some ideas how to do numbers 21, 25, 31, and 33 in Chapter 2 of the OER College Physics text here. So I copied and pasted this. Some of the formatting didn't go all that well, so you'll have to kind of bear with me on this. So for example, this 1 millisecond, this is 10 to the minus 3. That's supposed to be a power. All right, so number 21, it says a well-thrown ball is caught into a padded mitt. If the deceleration of the ball is 2.10 times 10 to the, I'm suspecting this was supposed to be, no, that probably looks right. Okay, 2.10 times 10 to the fourth meter per second squared, and it took 1.85 milliseconds from the time the ball first touches the mitt. Well, first of all, you know, physics people, we don't like the term decelerate. If the acceleration of the ball, I'm going to change that to 2.1 times 10 to the fourth meter per second squared, taking note that the acceleration is in the opposite direction of the velocity. And the question is, you know, what do we do with this, or how we analyze this? So what you want to be doing probably with all of these problems is start with a velocity graph. Just a sketch here. Velocity against time. The velocity graph is a very, very useful graph because once you have that, you know that the slope is equal to the acceleration and the area is equal to your distance or your change in position. So typically once you have the graph, the idea is to use these to write equations that describe the problem. So this ball, you know, if I start with a picture here, had some sort of velocity. And I don't think we know that. I don't see that in the problem here. I may not have gotten the entire thing when I converted it over, but and then it comes in contact with the mitt. Now it doesn't actually move this far in the picture, but I'm going to go ahead and kind of exaggerate that distance. It moves some sort of delta x in the problem. I don't think that's known either, but that's okay. And then it has a velocity of 0. So at t equals 0, we're up here on this graph. And this is going to equal whatever our initial velocity is, which I don't think we know. Okay, 1.85 milliseconds later. Now that's 0.00185. So on the graph here, 0.00185 seconds. Where you put this horizontally doesn't really matter in your sketch. If we assume constant acceleration, we get a graph that looks like this. Now, we can write two equations for this. One, the acceleration, which we know. I'm just going to put minus a here, where the a is the acceleration, this numerical value right here, is equal to, now if we go from here to here, this rise is what I call v sub o, but it's a drop in velocity, so let's put minus v sub o over delta t. This would be the delta t. So this equation right here has only one unknown. The acceleration is a known value, the delta t is a known value. That's going to allow you to get this. And I'm sure it probably says something about a distance. If it does, that's equal to that area right there. So that's going to be 1/2 base times height. That should be enough to answer that question. Take a look at number 25. Let's see, at the end of the race, a runner decelerates from a velocity of 9 meters per second at a rate of 2 meters per second. Again, physics people, we don't like the word decelerates. The runner accelerates from a velocity of 9 at a rate of, let's just say this, minus 2 meters per second, assuming the velocity is in the positive direction. So this is going to be very similar to the last one. Start with a velocity graph. And the first point on the graph is going to be 0.9, right? 9 meters per second, given in the problem. Now, I presume here that this person is going to be stopped, right? It's the end of a race. They would typically stop here. So sometime later, and I don't think we know the time, but we do know that they would end up with a final velocity of 0. Then we assume constant acceleration. And there's two equations we can write, right? One using slope, one using area. Now slope. rise over run. The rise here is -9 meters per second. Over a run, I just called that t, equals -2 meters per second. That's going to allow you to find the time. Now, that time could be bigger than 5 or less than 5. I suspect it's going to be less than 5. That means on this graph, 5 is like here somewhere. So, to get the how far, you're going to want this area, and you're going to want to use that calculated time, not the 5 seconds, right? And then final velocity is 0, probably. Now, the other thing that could conceivably happen is perhaps this t ends up after the 5, like this. Well, the first part of the problem you're going to work to be exactly the same. However, the how far part, then what you would do is at 5 seconds, you'd have to calculate the area of that trapezoid. And then to find the final velocity, you'd have to write an equation for this line and put your numerical value in. So give this a try, and you can ask about it in class. But those are the two possibilities for how that can occur. I suspect what will happen is this time is going to end up to be less than the 5 seconds. 31, let's see, a swan gets airborne by flapping its wings and running on top of the water. It must reach 6 meters per second to take off. It accelerates from rest at an average value of 0.35 meters per second. So we've got a swan here. That's going to be my swan. And it's accelerating, so my motion diagram would look like this. Remember, these are like snapshots in time. The swan's moving faster and faster and faster, so these delta x's are getting bigger and bigger and bigger. Right? The velocity vectors would be getting bigger and bigger and bigger as well. So how do we do this one? Right? Well, the answer to that's the same as the last two. Start with a velocity graph. You should be, draw nice big graphs on your paper, though. Like top third of your paper for your pictures and work. It starts from rest, so that goes through 0, 0. Sometime later, it's going to be moving 6 meters per second. Whoops, so sometime t. Yeah.
Oh, do you have Carol's phone number?
Yeah, I do. So I'm going to pause this for a second, what I'm doing here. Okay. Yep. Hopefully the sound still worked there. I had to pause that because I had somebody needing something. But anyway, all right. So now I kind of forgot where I was here. Swan, lake, airborne, acceleration. Okay, 6 meters per second. So getting back to this graph, sometime later, we know that the velocity is 6 meters per second. Oops. And again, we'll assume constant acceleration, which means a linear graph. Now you can write two equations for this, one for slope, one for area. So when we go from here to here, the rise is 6, the run is t, and the acceleration is given to be this value. That's going to allow you to solve for t, which is the answer to B. And then where it says how far, that's this area right here. That's going to be 1/2 base times height. Okay, 33. Football player collides with a goalpost while running 7 meters per second, comes to a full stop. Just like the previous problems, draw a velocity graph. At t equals 0, the football player is going 7.5 meters per second. Sometime later, the velocity is 0. Connect the dots. Then we can write two equations, one for slope, one for area. Slope, we're going down 7.5 over t, and that's equal to the acceleration. I think that's going to have a couple of unknowns. Area, 1/2 t times 7.5 is going to equal this distance. That's going to allow you to calculate t. Once you have t, you can go back to your slope equation, and you'll be able to get the acceleration. Oh, looks like that's it. All right, so hopefully the sound on this came out. I apologize for having to stop it right in the middle there. Sometimes when I stop these videos, the sound quits working, but hopefully this one's okay. Have a great day.